What if I told you that an American research lab just quietly solved one of the single biggest engineering problems standing between today's fragile quantum computers and tomorrow's genuinely useful ones, and neither China nor Europe, despite years of pouring billions of dollars into this exact same race, actually got there first? That is not an exaggeration for the sake of a dramatics. Opening line. It happened this week. It was published in one of the most prestigious scientific journals on the planet, and it is already triggering a wave of corporate consolidation among the biggest names in American technology, catching researchers on 2 other continents genuinely off guard in the process. A quiet lab in Malibu. California just proved that a quantum computer can run itself, coordinating its own error correction with zero help from room temperature equipment, using a chip that can be manufactured on a completely ordinary commercial production line. Stay with me, because by the end of this video you will understand exactly why this milestone matters, and why it just reshuffled the entire global order of who is actually winning the race to build a real, usable quantum computer. Let's start with the problem, because you cannot understand why this breakthrough matters until you understand just how broken the current approach to quantum computing really is. Every quantum computer you have ever seen a picture of, the ones that look like glowing golden chandeliers hanging inside a metal tube, is actually a tiny quantum chip connected to a massive forest of wires and electronics sitting outside the freezer. Those qubits, the basic units of quantum information, are incredibly fragile. They only work when they are cooled down to temperatures colder than deep space, hundreds of times colder than the vacuum between stars. To control them, engineers send electrical signals down individual wires from room temperature equipment through the walls of a refrigerator and down into that frozen chip. Every single qubit in that chip needs its own dedicated wire or set of wires running from the warm outside world all the way down to the freezing core. A machine with 50 qubits might already need hundreds of individual connections. Now imagine trying to scale that up to the thousands or millions of qubits that a truly powerful quantum computer will eventually need. You would need so many wires that they physically could not fit inside the refrigerator anymore. On top of that, every wire carries a tiny bit of heat down into the cold zone, and heat is the enemy of a quantum chip. Too much heat and the fragile quantum states collapse before they can do anything useful. Scientists all over the world have been calling this the wiring bottleneck for years, and it has quietly become one of the single biggest obstacles blocking quantum computers from ever becoming powerful enough to solve the problems we actually want them to solve, like discovering new medicines, cracking previously unbreakable codes, or modeling chemistry that today's supercomputers simply cannot touch. To really appreciate why this is such a stubborn problem, think about the difference between building one prototype car by hand in a garage and building 1 million identical cars on an assembly line. The garage prototype can be delicate, expensive, and packed with custom parts that only exist as one-off pieces. A factory line demands something completely different. Every part has to be reliable, repeatable, and affordable at scale. For years, quantum computers, everywhere, regardless of which country was building them, looked a lot more like that hand-built garage prototype. Every additional qubit meant more custom wiring, more specialized equipment, and more delicate manual tuning by highly trained physicists. Here's the part that makes this story genuinely interesting from a global competition standpoint. This is not a problem American researchers were quietly working on, alone while the rest of the world ignored it. Research teams in Europe, particularly at institutions like TU Delft in the Netherlands, have been publishing serious, closely watched progress on exactly this control problem for years, including a widely cited demonstration back in 2021 showing that a cryogenic chip could generate control signals for multiple qubits at once. European researchers, working across a dense network of universities and national laboratories, including EPFL in Switzerland and CERN, have arguably produced more foundational scientific papers on cryogenic control electronics, sometimes called cryo-CMOS, than any other region on Earth. China, meanwhile, has invested heavily in its own version of this same race, and Chinese researchers have recently filed patents on cryogenic circuit designs specifically intended for quantum computing applications, signaling a clear intent to compete seriously on this exact technical front rather than simply focus on headline-grabbing qubit counts. So if Europe has been publishing foundational research on this exact problem for years, and China has been actively filing its own patents in the same space, why did an American lab most people have never heard of end up being the one to actually cross the finish line first, with a complete, working manufacturable system? That is exactly the question worth digging into, because the answer says a lot about the difference between publishing an impressive scientific paper and actually building something a factory could produce by the thousands. This is where HRL Laboratories comes into the story, and if that name does not ring a bell, do not worry. Because until this week, most people outside the semiconductor world had never heard of them either. HRL is based in Malibu, California, on a research campus with a genuinely wild pedigree. This is the same site where engineers invented the self-aligned gate MOSFET, the tiny transistor structure that quietly became the foundation of almost every microchip made on the planet today. This is also the site where the world's very first laser was built. In other words, this is not some random startup chasing hype. This is a lab with a track record of inventing the unglamorous foundational technology that later ends up underneath everything else in the industry. For years, HRL has been jointly owned by two giants you would not necessarily expect to be deep in the quantum computing race, Boeing and General Motors. That ownership alone tells you something important. This was never a lab chasing headlines or trying to impress, was a research organization quietly working on foundational hardware, the unglamorous plumbing of quantum computing, while other labs around the world, in Europe, in China, and across the rest of the United States, fought very public battles over who had the most qubits, or the flashiest press release. So what did HRL actually build? In a paper published this week in the scientific journal Nature, one of the most respected and rigorously peer-reviewed journals in all of science, HRL researchers described a quantum processor built from silicon that can essentially run itself. Instead of relying on racks of external electronics sitting at room temperature to generate every single control signal, HRL engineered a custom control chip that lives inside the refrigerator itself, right next to the qubits, operating at a mind-bending negative 450 degrees Fahrenheit. That is barely a few degrees above absolute zero, the coldest temperature theoretically possible in the entire universe. This custom chip is built using standard complementary metal oxide semiconductor technology, the same basic manufacturing family used to build ordinary computer chips found in your phone or your laptop. That detail matters enormously, and I want you to really sit with it for a second. European researchers had already proven the underlying physics could work in a laboratory setting. HRL did something different and arguably harder. They built their controller using a process that can be manufactured at a normal commercial chip foundry, the same kind of factory that already mass produces chips for everyday electronics. That is the difference between a brilliant one-off laboratory demonstration and something you could eventually manufacture by the millions. And it is exactly the gap that had been separating years of promising European and academic research from an actual deployable product. The device HRL demonstrated houses 18 working qubits, built on top of an array of 54 quantum dots fabricated on 200mm silicon germanium wafers, the same wafer size widely used across the commercial semiconductor industry. It helps to understand a little bit about what a quantum dot actually is, because that term is going to keep coming up. A quantum dot is essentially a tiny trap for individual electrons, created inside a silicon chip using precisely patterned electrodes that squeeze electrons into an extremely small physical space. Once you can trap a single electron reliably, you can use its quantum spin, essentially a tiny, built-in direction it can point, as the actual unit of quantum information. HRL's device configures up to 18 of these quantum dots as what scientists call exchange-only qubits, a specific style of spin qubit that gets manipulated using purely electrical signals rather than more complicated microwave pulses, a detail that made this whole system considerably easier to integrate with a fully local cryogenic controller in the first place. And here's the truly remarkable part. The custom control chip sitting inside that freezing environment generated every single signal needed to run the system, and it executed quantum error correction completely on its own, with zero real-time input from any room temperature equipment. Quantum error correction, for anyone unfamiliar, is essentially the immune system of a quantum computer. Qubits are so fragile that they constantly pick up tiny errors from their environment, and without a system constantly detecting and correcting those errors, a quantum computer simply cannot ruin any calculation long enough to be useful. Getting error correction to run autonomously inside the cold zone without constant help from the outside world is considered one of the essential milestones on the road toward a genuinely practical quantum computer. And nobody, not in Europe, not in China, not anywhere else in the United States, had previously demonstrated a complete system doing it quite this way. To physically connect this frozen control chip to the qubits without reintroducing the wiring nightmare they were trying to escape, HRL engineers had to solve an entirely separate hardware puzzle. They developed a high-density ribbon cable made from superconducting niobium layered onto polyimide, carrying nearly 300 separate channels through a single flexible strip, instead of hundreds of individual bulky wires. Superconducting materials carry electrical signals with essentially zero resistance at these extreme temperatures, which means the connection can carry enormous amounts of information without dumping unwanted heat into the fragile quantum environment. It is a small piece of engineering, easy to overlook in a headline, but it is exactly the kind of unglamorous solution that turns a laboratory demonstration into something that could genuinely scale. Put all of these pieces together, and what you get is the first complete prototype of an architecture where the qubits, the control logic, and the high-density connections between them can all be manufactured using standard commercial semiconductor processes and can all fit inside a single ordinary cryogenic refrigerator. Rob Vasquez, the president and chief executive officer of HRL Laboratories, explained the philosophy behind this approach by pointing out that the technologies which eventually won in conventional computing were never simply the highest performing options available. They were the ones that could actually be manufactured cheaply and at massive scale. HRL is betting that quantum computing will follow the exact same historical pattern, and that the winners of this new industry will not necessarily be whoever has the single most impressive qubit on a lab bench, but whoever can actually build a factory that reliably churns out working quantum hardware, no matter which continent that factory eventually sits on. Now, here is where the story gets even more interesting, because this breakthrough did not happen in a vacuum, and it is landing at an extraordinary moment for HRL as a company. Just this week, alongside the Nature publication, news broke that IBM is finalizing a deal to acquire HRL Laboratories from its longtime owners, Boeing and General Motors. Think about the timing of that for a second. One of the largest and most established players in the entire quantum computing industry is moving to acquire this exact lab with this exact self-running silicon architecture, right as the results are being published in one of the most prestigious scientific journals on the planet. IBM has spent years building its quantum computing strategy primarily around superconducting qubits, a completely different physical approach from the silicon spin qubits that HRL specializes in. By bringing HRL's silicon spin technology and cryogenic control expertise in-house, IBM is effectively giving itself a second, parallel path toward building large-scale quantum computers, rather than betting the entire company on a single qubit technology. Silicon spin qubits, the kind HRL builds, have a genuinely compelling advantage over some competing approaches because they can be manufactured using tools and processes that are already extremely close to the standard chip-making techniques used across the semiconductor industry, and they take up dramatically less physical space per qubit than some rival technologies. If you are enjoying learning about breakthroughs like this one, now would be a great time to hit like and subscribe, because we cover stories like this the moment they happen, long before they hit the mainstream news cycle. Let's talk more specifically about why Europe, despite years of genuine scientific leadership in this exact field, did not end up crossing the finish line first. European research groups, spread across a dense network of universities in the Netherlands, Switzerland, France, and beyond, have consistently produced some of the most cited academic papers on cryogenic quantum control electronics anywhere in the world. Researchers there have demonstrated cryo-CMOS chips capable of generating control signals for multiple qubits, have built cryogenic multiplexers to reduce wiring overhead, and have published detailed device models describing exactly how ordinary transistors behave at temperatures close to absolute zero. That is genuinely impressive, foundational scientific work, and much of the underlying physics HRL and every other serious quantum hardware company relies on today in every country pursuing this technology traces directly back to European laboratories. Consider just how much of the foundational groundwork actually originated in Europe specifically. A landmark 2021 paper, widely cited across the entire field, demonstrated CMOS-based cryogenic control of silicon quantum circuits, essentially proving years before HRL's announcement that a chip operating in the cold zone could reliably generate control signals for multiple qubits simultaneously. Follow-up work at various European institutions pushed that concept further, demonstrating increasingly sophisticated cryogenic demultiplexers, cryogenic digital to analog converters specifically designed for biasing spin qubits, and even cryogenic routers capable of directing control signals to different parts of a qubit array without requiring a separate physical wire for each individual connection. Some of this research even achieved dissipation levels low enough to operate comfortably within the tightly constrained power budget available inside the coldest parts of a dilution refrigerator, an impressively difficult engineering feat in its own right. If you had been tracking published academics, literature on this topic over the past 5 years, you would have every reason to expect a European institution to be the one crossing this particular finish line first. But there is a meaningful difference between demonstrating that a technique works in a university laboratory setting and building a complete integrated system using components that a commercial semiconductor foundry could mass produce tomorrow. European quantum research has historically been organized primarily around academic institutions and national laboratories, brilliant at generating foundational insight, but not always structured, funded, or incentivized in the same way as a dedicated industrial research lab explicitly built to hand its inventions directly to commercial chip manufacturers. HRL, by contrast, has spent decades as exactly that kind of industrial research organization, with its own on-site fabrication cleanroom and a direct institutional memory of taking laboratory-scale inventions all the way through to mass manufacturable products, going all the way back to the transistor itself. That structural difference, industrial lab versus academic consortium, appears to be a meaningful part of why the complete manufacturable end-to-end system arrived first out of Malibu rather than out of Delft, Lausanne, or Geneva. China's story is a little different and arguably even more surprising. China has poured enormous public investment into quantum computing over the past decade. And Chinese researchers have achieved genuinely remarkable headline results, including record-breaking photonic quantum demonstrations that have made global news, with prototypes solving highly specialized mathematical sampling problems in microseconds, tasks that researchers estimated would take the world's fastest classical supercomputers an almost incomprehensible span of time to complete. China has also built out an entire commercial quantum computing ecosystem, with spin-out companies selling smaller-scale quantum computing systems to businesses and releasing their own domestically developed quantum computer operating systems for public download. But China's cryogenic control chip research specifically, based on publicly available patent filings and published papers, appears to be at an earlier stage in this narrow corner of the field. Recent Chinese patent activity in this space has concentrated more around scientific instrumentation readout circuits, wideband radio frequency circuits designed to compensate for frequency drift at extreme cold, and foundational device characterization work describing how transistors behave at cryogenic temperatures, rather than a complete, deployed, autonomously operating control architecture already integrated with a working qubit array performing genuine error correction. In other words, China has been racing hard on qubit performance and specialized quantum demonstrations, the kind of results that generate spectacular headlines and dominate international coverage, while a quieter, less glamorous engineering race over how to actually control and manufacture those qubits at scale was happening somewhere else entirely, largely out of the public eye and almost entirely absent from the kind of press coverage that China's more dramatic physics demonstrations tend to attract. It is worth noting that China's own quantum computing strategy has explicitly prioritized different physical approaches than the silicon spin qubits HRL specializes in, with the country's most celebrated results coming primarily from photonic systems using particles of light and superconducting systems using loops of superconducting metal, rather than the silicon-based spin qubit architecture at the center of HRL's breakthrough. That divergence in strategic focus does not necessarily mean China is behind in some absolute sense across the entire quantum computing landscape, but it does mean that specifically in this narrow, unglamorous corner of cryogenic control engineering, the milestone HRL, just achieved, caught Chinese quantum research institutions, focused predominantly elsewhere, on a genuinely different technical bet entirely. It is worth being honest and balanced about what this breakthrough does and does not prove. 18 qubits is still a very small number compared to the thousands or millions of qubits that would be needed for the truly world-changing applications people talk about, like breaking modern encryption or simulating complex drug molecules with full accuracy. This result is a milestone in control architecture and manufacturability, not a finished, world-beating quantum computer ready to ship tomorrow. And it does not automatically mean the United States has permanently locked in victory in this broader race. And turning this proof of concept into a machine with thousands or millions of reliable qubits will still take years of additional engineering, funding, and frankly, a fair amount of trial and error, and both European and Chinese research groups remain entirely capable of catching up or leapfrogging this specific architecture with their own future innovations. Still, it is genuinely hard to overstate how significant it is that the first complete, manufacturable, autonomously operating quantum control system emerged from an American industrial lab, at the exact moment IBM moved to acquire it, while European institutions were still primarily publishing academic papers and Chinese researchers were still filing early-stage patents in the same narrow technical corner. There is another layer to this story that most casual observers might miss entirely. Earlier this year, the government announced plans to award roughly $1 billion to IBM to help establish a new quantum chip foundry in New York, a facility intended to serve not only IBM's own internal quantum computing efforts, but outside customers as well. According to reporting on the acquisition, HRL's chip production, which has historically happened at its own facility in California, is expected to shift over to that same IBM facility in New York in the near term. So, you are watching multiple massive forces converge at exactly the same moment. A scientific breakthrough proving self-running quantum chips are actually possible. A major acquisition folding that technology into one of the biggest names in computing, and a brand new billion-dollar domestic manufacturing facility built specifically to produce this next generation of quantum hardware at scale, all while Europe and China are still working through earlier stages of the exact same underlying engineering problem. Let's zoom out for a moment, because I want you to understand why engineers across the entire quantum computing industry on every continent have been chasing this exact problem for years, and why HRL's result is being treated as such a genuine milestone rather than just another incremental press release. Research groups all over the world at universities and inside major technology companies alike have published papers for years describing the same fundamental challenge in different words. As quantum computers scale toward the thousands or millions of qubits required for truly transformative applications, the sheer number of individual wires needed between room temperature control equipment and the frozen quantum chip becomes physically unmanageable. Some researchers have experimented with moving digital control circuits partway into the cold zone. Others have explored superconducting digital electronics operating at extremely low temperatures. And some teams, particularly in Europe, have even investigated wireless communication links inside the refrigerator itself as a way to avoid physical wiring altogether. Each of these approaches represents a different attempt to solve the exact same underlying puzzle. How do you control an enormous number of extremely fragile qubits without drowning the whole system in cables, heat, and cost? What makes HRL's demonstrations stand out from this broader wave of international research is not that they were the very first team anywhere on Earth to ever think about moving control electronics into the cold zone. European groups explored pieces of this puzzle years earlier. What stands out is that HRL appears to have assembled a genuinely complete working system, qubits, control chip, and interconnect, all fabricated using processes compatible with existing commercial semiconductor manufacturing, and successfully demonstrated it running one of the single most important operations a quantum computer will ever need to perform: error correction entirely on its own. That combination of completeness and manufacturability is precisely why this result was considered significant enough to publish in Nature, and precisely why a company like IBM would move to acquire the lab, responsible for it before anyone in Europe or China could claim the same milestone first. It is also worth pausing to appreciate just how much of an engineering marathon this really was behind the scenes. Getting ordinary electronic circuits to function correctly at temperatures close to absolute zero is nowhere near as simple as just placing a normal chip inside a very cold box. Materials behave differently at those temperatures. Transistors switch differently. Signal timing shifts. Engineers have to essentially reinvent decades of established chip design intuition for an environment where almost nothing behaves the way it does at room temperature. HRL's team had to design a custom controller specifically built to function reliably at these extreme conditions while still being manufacturable on a completely standard commercial production line, which is an extraordinarily narrow needle to thread. Building something exotic enough to survive near absolute zero while still being ordinary enough to mass produce is exactly the kind of unglamorous, deeply difficult engineering work that rarely makes headlines, but ends up being the actual foundation. Everything else gets built on top of, and it is precisely the kind of work that a well-resourced industrial lab, rather than a purely academic consortium, tends to be best positioned to finish first. There is a helpful historical parallel here if you think back to the earliest days of classical computing, and it is worth remembering that this exact pattern, foundational research emerging from one region while manufacturable products emerge from another, has actually played out before. The very first computers were enormous, room-filling machines that required teams of specialized technicians constantly monitoring, vacuum tubes, swapping components, and manually feeding instructions into the system. Computing only became a genuine mass-market technology once engineers figured out how to shrink all of that complexity down into a single, reliable, mass-manufacturable chip, the microprocessor, that could essentially run itself once it was powered on. And it was American industrial labs working closely with commercial semiconductor manufacturers that ultimately delivered that transition into mass production, even though foundational transistor physics research had been genuinely global. Quantum computing today feels a lot like those early room-filling computers, delicate, heavily dependent on constant expert supervision, and nowhere close to something you could simply plug in and use, regardless of which country's laboratory happens to be running it. HRL's self-running architecture is a small but genuinely meaningful step toward quantum computing's own version of that same historic transition, moving away from constant external supervision and toward a self-contained system that can simply do its job, manufactured on the same kind of production lines that already build the ordinary chips inside your phone. So why should any of this matter to you if you are not a physicist or an engineer working inside a clean room, and if you have no particular stake in which country wins this race? Because quantum computing, if it ever reaches its full potential, is not just an academic curiosity. It is a technology with the potential to completely reshape entire industries, and whichever country manages to actually manufacture reliable, scalable quantum hardware first stands to gain enormous economic and strategic advantages for decades to come. Drug companies are hoping quantum computers will eventually simulate complex molecules well enough to discover new medicines far faster than today's methods allow. Materials scientists are hoping quantum simulations will help design dramatically better batteries and more efficient solar cells. Financial institutions are watching closely because certain optimization problems in finance could theoretically be solved dramatically faster with quantum hardware. And on the more concerning side, cryptographers have been warning for years that a sufficiently powerful quantum computer could eventually break some of the encryption schemes that currently protect global banking, communications, and government secrets, which is exactly why governments and militaries in the United States, across Europe, and in China are all pouring enormous resources into this race simultaneously. Think about drug discovery for a moment, because it is one of the clearest examples of why this matters in a very human, very tangible way, regardless of which country ultimately builds the winning hardware. Designing a new medicine today often involves testing enormous numbers of candidate molecules, either physically in a lab or through massive classical computer simulations, a process that can take years and cost billions of dollars before a single new drug ever reaches a patient. The reason this process is so slow is that classical computers fundamentally struggle to accurately simulate the quantum mechanical behavior of complex molecules, because the molecules themselves are quantum mechanical systems, and classical bits simply are not built to represent that kind of information efficiently. A sufficiently powerful quantum computer, built from millions of stable, well-controlled qubits, manufactured at the kind of scale HRL's architecture points toward, could, in principle, simulate those molecular interactions directly and dramatically shrink the timeline for discovering new treatments, wherever in the world that machine ultimately gets built. If this breakthrough scales the way HRL and now IBM clearly believe it can, we may look back on this week as a genuinely important turning point, not just for quantum computing broadly, but specifically for the question of which region of the world actually ends up controlling the manufacturing backbone of this future industry. The wiring problem that has quietly limited quantum computing for years finally has a credible, demonstrated manufacturable solution, and it emerged from an American lab most people had never heard of, at the exact moment European institutions were still publishing academic milestones and Chinese researchers were still filing early patents in the same narrow technical corner. One of the biggest names in the entire technology industry just moved decisively to make sure America owns a piece of it before anyone else could. Before you go, if you want to stay ahead of breakthroughs like this one, the ones that will eventually shape headlines everywhere but are happening quietly right now, make sure you like this video and subscribe to the channel, because this is exactly the kind of story we dig into first. It is genuinely rare to watch a foundational engineering problem get solved and a massive corporate acquisition happen in the very same week, and it is even rarer for both of those events to be tied to a single small lab that most people in America, in Europe, or in China had never heard of before now. 10 years from now, when quantum computers might be helping design life-saving drugs or optimizing global supply chains in ways we can barely imagine today, there is a real chance people will trace part of that progress back to this exact moment. A quiet publication in Nature out of a research campus in Malibu that has been quietly inventing foundational technology since the earliest days of the laser, while research teams an ocean away in Europe and across the Pacific in China were left studying exactly how they got beaten to a milestone they had every reason to expect to reach first themselves. Quantum computing has spent decades living inside laboratories, surrounded by cables, refrigerators, and racks of delicate equipment, with research teams across America, Europe, and China all racing toward the exact same finish line. This week, a quiet lab in Malibu just proved that a quantum chip can run itself. One of the biggest companies in computing just decided that future was worth buying. And both Europe and China are now left racing to catch up to a milestone they genuinely did not see coming.